It is 1942, on a test stand at a brand new factory in Decatur, Illinois, a plant that 6 months earlier had been an empty field. A cluster of engineers in coveralls stands a cautious distance from a 9-cylinder radial engine bolted into a test rig, the same basic shape of engine that has been thundering out of American aircraft plants by the thousand, the same engine that lifts B-17 flying fortresses off runways and drags Douglas DC-3s across the country. A technician signals, and the starter motor turns the crankshaft over. The engineers are listening for something specific, something that has nothing to do with horsepower or torque. They are listening for the absence of a sound. In a gasoline radial, the engine catches with a bark, a spark-ignited crack of combustion, cylinder after cylinder, unmistakable. What fires on this stand does not bark, it thuds. A deeper, heavier, more deliberate concussion, cylinder after cylinder, with none of the electrical sharpness of a spark plug's crack. There is no spark plug on this engine at all. The fuel is igniting itself, crushed into fire by compression alone, inside cylinders that started life in a Wright aeronautical drawing meant only for high-octane aviation gasoline and a magneto. The engineers are from the Caterpillar Tractor Company, a firm that has spent its entire existence building bulldozers and tractors, not aircraft engines and not tank engines, and they have just done something that nobody at Wright Aeronautical, nobody in Detroit, and nobody in the War Department was entirely sure could be done. They have taken a proven mass-produced gasoline aircraft radial, the Wright R-1820 Cyclone 9, the engine of the B-17, and they have converted it, cylinder by cylinder, into a diesel. Not swapped it out, not paired two of them together, converted the actual combustion process at its core from spark ignition to compression ignition while keeping as much of the original architecture as they possibly could. This was not a story about America lacking an engine. By 1942, the Sherman already had engines, several of them, flawed and improvised but real. This was a story about America wanting something more specific and much harder. An engine that could run on diesel fuel, built from the bones of an engine that had never been designed to. The other Sherman engine stories all share a common shape. The Army needed a tank engine and it did not have one, so American industry improvised with what it already had. Continental supplied an aircraft radial because there was nothing else available. Chrysler bolted 5-car engines together because that was what its factories already tooled. Ford cut 4 cylinders off a failed aircraft V12 because the failed engine was sitting idle. General Motors coupled 2 bus diesels together because the bus diesel already existed and already worked. In every one of these stories, the problem was scarcity, the absence of a suitable engine, and the solution was combination or substitution, taking existing whole engines and rearranging them. The Caterpillar story is a different kind of problem entirely, and it deserves to be told differently. By 1941, the Sherman was not lacking for engines. The radial was flowing from Continental, the diesel twin was in development at General Motors, the Ford V8 was on its way. What the Ordnance Department wanted from Caterpillar was not another whole engine pulled from an existing supply. It wanted a specific, difficult, surgical transformation, the conversion of an engine's fundamental combustion chemistry, and it wanted that transformation performed on the internal architecture of an aircraft engine that had been designed, from its first drawing, around an entirely different kind of fire. This is a story about rebuilding an engine's soul while keeping its skeleton, and it produced one of the strangest, least remembered, and most completely vanished variants of the Sherman tank ever built. Here is the paradox. Diesel engines and gasoline engines are not two flavors of the same machine, easily swapped by changing the fuel in the tank. They are two fundamentally different ways of making fire happen inside a cylinder, and the difference reaches into nearly every physical dimension of the engine. The strength of the pistons, the shape of the combustion chamber, the pressure the crankcase must survive, the entire architecture of how fuel gets into the cylinder and when it burns. Taking a gasoline engine and making it run on diesel fuel is not a modification. In the fullest sense, it is closer to keeping an animal skeleton and rebuilding every organ inside it. And yet, that is exactly the assignment the War Department handed to a construction equipment company in July of 1941, and that is exactly what Caterpillar delivered. The resolution of this paradox lies in a distinction that the finished engine embodied perfectly. Caterpillar did not build a new engine from nothing, and it did not merely modify an existing one. It performed a kind of engineering triage, identifying which parts of the Wright Cyclone's architecture could survive the transformation to diesel unchanged, and which parts had to be torn out and rebuilt from first principles to survive the violence of compression ignition. Understanding exactly where that line fell, what stayed and what changed and why, is the whole engineering story, and it is a story the popular histories of the Sherman have almost never told because the vehicle it produced was so rare, so short-lived, and so completely erased from the physical record that it is easier to skip than to explain. Asked most people to name the engines of the Sherman tank, and if they know the subject at all, they will name 3 or 4. The Continental Radial, the Ford V8, the Chrysler Multibank, the General Motors twin diesel. Almost nobody names the 5th, the Caterpillar-built diesel Radial that powered the M4A6, because almost nothing survives to remind anyone it existed. No M4A6 tank survives today, anywhere, in any museum, in any collection. No example of the RD-1820 engine survives either. The variant that this entire engineering effort produced has vanished as completely as a weapon system can vanish, leaving behind only paperwork, a handful of photographs, and the memory of engineers who are long since gone. This is precisely why the story deserves to be told, because the engineering achievement at its center, the conversion of a mass-produced gasoline aircraft Radial into a working diesel, was genuinely remarkable, and because the reason it disappeared has almost nothing to do with whether it worked. The popular history, to the extent it mentions the M4A6 at all, treats it as a footnote, a curiosity, 75 tanks, and then nothing. What it misses is the specific mechanical problem Caterpillar solved, the difference between an engine that merely runs on diesel fuel and an engine that has been correctly redesigned to survive diesel combustion, and the specific, almost absurd reason that a program which by every account worked was shut down anyway. This is a story about an engine that succeeded and was killed by success elsewhere. To understand why anyone bothered with this transformation, you have to remember what diesel offered a tank in the first place, the same virtues that had already pushed General Motors to bolt 2 bus engines together for the M4A2. Diesel fuel has a higher flashpoint than gasoline, making a diesel tank harder to set alight when it is hit. Diesel combustion needs no ignition system at all, no spark plugs, no distributor, no magneto, no carburetor, an entire category of failure simply engineered out of existence. And diesel engines, because they compress their air far harder before combustion, extract more energy from every gallon of fuel, giving a diesel tank meaningfully greater range on the same fuel load. These were not abstract advantages. They were the difference between a tank that could go further before refueling and a tank that was less likely to become a coffin when an armor-piercing round found it. But there was a second, more specific motivation behind the Caterpillar program, distinct from the reasoning that had produced the GM twin diesel. The Wright R-1820 Cyclone, the donor engine Caterpillar was asked to convert, was not some minor aircraft power plant. It was one of the most important aircraft engines in the entire American war machine, the engine at the heart of the B-17 Flying Fortress, the 4-engine heavy bomber that formed the backbone of the American daylight bombing campaign over Europe. And it also powered the Douglas Dauntless dive bomber and the DC-3 transport that would become the military C-47. An engine that important was going to be needed by the aircraft industry in numbers that dwarfed anything a tank program could compete for. If a diesel tank engine could be built using the R-1820's proven architecture as a starting template, built in its own dedicated factory, separate from Wright's own production lines, the tank program would get the benefit of a mature, well-understood design without drawing a single engine away from the bombers that needed it. The choice of Caterpillar to perform this conversion looks strange at first glance, and it is worth pausing on why the War Department picked a construction equipment manufacturer for a problem this specialized. Caterpillar built bulldozers, tractors, and heavy earth-moving equipment, not aircraft, not tanks. But Caterpillar possessed something that mattered more than experience with weapons: deep, hard-won institutional expertise in diesel engines specifically, because diesel power was the beating heart of the entire construction equipment industry. Its engineers had spent decades solving exactly the kind of problems a diesel conversion would demand: how to design pistons and cylinder heads that could survive the punishing pressures of compression ignition, how to build fuel injection systems that would deliver diesel fuel precisely, how to engineer a crankcase and bearings strong enough to survive combustion forces a gasoline engine of similar size never had to withstand. This was exactly the specialized knowledge that Wright Aeronautical, a company built entirely around gasoline aviation engines, did not possess. The War Department's insight, in July of 1941, was to split the problem in two and hand each half to the company best equipped for it. Wright had already solved the aerodynamic and mechanical problem of building a light, powerful, reliable air-cooled Radial, the R-1820, tested over a decade of aviation service. Caterpillar had already solved the combustion problem of making compression ignition work reliably at scale. The assignment was to marry the two, taking Wright's proven mechanical architecture and rebuilding its internal combustion chemistry using Caterpillar's diesel expertise. It was an unusual pairing, but it made a strange kind of sense, and Caterpillar accepted the challenge. Before we can appreciate what Caterpillar actually did, we have to understand why the conversion was hard, why an engineer cannot simply swap the carburetor for an injector and call a gasoline engine a diesel. The difference begins with how the two engines ignite their fuel. A gasoline engine compresses a mixture of air and fuel together at a relatively modest compression ratio, and then ignites that mixture deliberately, at a precise instant with the electric spark from a spark plug. The compression ratio has to stay modest because gasoline compressed too hard will ignite on its own, prematurely, a phenomenon called detonation or knock, which can destroy an engine in seconds. The whole architecture of a gasoline engine, including the shape of its pistons and its combustion chamber, is built around staying safely below that self-ignition threshold and letting the spark plug decide exactly when combustion begins. A diesel engine does the opposite on purpose. It compresses air alone, without any fuel present, to a far higher ratio, so high that the air's temperature climbs to well over 1,000 degrees Fahrenheit purely from being squeezed. Only then, at the top of the compression stroke, does the engine inject fuel directly into that superheated, high-pressure air, and the fuel ignites itself instantly from the heat of compression with no spark required at all. This means a diesel piston and connecting rod and crankshaft and bearings must survive combustion pressures that can run 2 to 3 times higher than a comparable gasoline engine ever generates, because the compression ratio itself is so much greater, and because the combustion event is more violent. A gasoline piston asked to survive diesel compression will crack. Gasoline connecting rods and crankshaft bearings asked to survive diesel peak pressures will fail. This is why converting the R-1820 to diesel could never be a matter of new fuel lines and a different pump. It required rebuilding every component that touched the violence of combustion, while, if possible, preserving everything that did not. This is the heart of Caterpillar's engineering triage, and it is worth being specific about exactly what survived the transformation from the original Wright design. Caterpillar kept the cylinders, the individual finned steel barrels that the pistons moved inside, because the basic geometry of an air-cooled cylinder, exposed to the wind and ribbed with cooling fins, did not need to change to accommodate diesel combustion, only what happened at its top and bottom. Caterpillar kept the crankshaft, the single, short, centrally located shaft that all 9 cylinders drove through the same ingenious master rod and articulating rod arrangement common to every radial engine, in which one piston's connecting rod attaches directly to the crank throw, and the other 8 attach in a ring to that master rod. And Caterpillar kept the supercharger, the gear-driven air pump that forced pressurized air into the cylinders, retaining its basic mechanical design even as its job within the engine changed. Keeping these 3 elements, the cylinders, the crankshaft, and the supercharger, was not laziness or shortcut taking. It was the correct engineering decision, because none of these components was fighting the physics of diesel combustion directly. The crankshaft absorbs whatever force the connecting rods deliver to it, whether that force comes from a gentler gasoline explosion or a harder diesel one, as long as the crankshaft itself and its bearings are built strong enough for the higher loads, which Caterpillar's diesel expertise let them calculate and reinforce with confidence. The cylinder barrel simply contains the piston's stroke and carries away heat through its fins, a job that does not care what kind of fuel is burning inside it. By preserving these proven, already tooled, already understood components, Caterpillar saved enormous amounts of engineering time and manufacturing setup, concentrating its real work on the parts of the engine that actually had to be rebuilt from the ground up to survive compression ignition. The parts that had to change were the parts that lived at the exact site of combustion, and Caterpillar rebuilt every one of them. New pistons were designed, shaped, and strengthened to survive the far higher compression ratio and the far more violent pressure spike of diesel ignition, their crowns very likely reshaped to help control how the injected fuel spray mixed with the compressed air, a detail that matters enormously in diesel combustion because unlike a gasoline engine where the air-fuel mixture is already blended before ignition, a diesel engine has only the fraction of a second between injection and combustion to mix fuel and air well enough to burn cleanly and completely. New cylinder heads were designed as well, because the gasoline head, built around a spark plug boss and a combustion chamber shaped for spark-ignited flame propagation, had no place in a diesel engine and no way to accommodate the injection equipment diesel combustion required. And Caterpillar designed an entirely new fuel injection and lubrication system because a gasoline Radial's carburetor, mixing fuel and air together before it ever reached the cylinder, was fundamentally incompatible with a diesel's requirement to inject fuel directly, at high pressure, at a precisely controlled instant into air that was already compressed and already hot. The lubrication system needed rework too, because the entire thermal and pressure environment inside a diesel cylinder differs enough from a gasoline cylinder that oil circulation, oil cooling, and the demands placed on bearing surfaces all shift accordingly. In sum, Caterpillar kept the outer shell and the structural skeleton of the Wright Cyclone and rebuilt, essentially from scratch, everything that determined how and when the engine actually caught fire. It was less a modification than a resurrection, the same body with a different heart. The specific method Caterpillar chose to injecting and igniting the fuel deserves its own explanation, because it was a genuinely different approach from the other diesel Sherman engine of the war, and understanding the difference is where the real mechanical insight lives. The General Motors twin diesel that powered the M4A2 used direct injection, spraying fuel straight into the main combustion chamber above the piston through a unit injector mounted right at the cylinder. Caterpillar's diesel Radial instead used indirect injection, built around a small pre-combustion chamber, a secondary antechamber connected to the main cylinder by a narrow passage. Here's how it worked. As the piston rose on its compression stroke, some of the compressed, superheated air was forced through that narrow passage into the small pre-chamber. At the precise moment of ignition, fuel was injected not into the main cylinder directly, but into this small antechamber, where it mixed with the trapped hot air and ignited first, in a confined, turbulent space far smaller than the main cylinder. The burning, expanding gases from that initial ignition were then violently forced back out through the connecting passage into the main combustion chamber, arriving as a hot, high-velocity jet that ignited and thoroughly mixed with the remaining air and fuel in the main cylinder, completing the combustion event. The pre-chamber, in effect, acted as a kind of ignition amplifier, using a small, controlled first burn to trigger and stir a larger, more complete second burn. This indirect injection approach had real advantages for an engine converted from an existing gasoline design under wartime time pressure. It was more forgiving of variations in fuel quality and injection precision than direct injection, and it tended to produce smoother, less violent combustion than firing fuel directly into a large open chamber, which mattered for an engine whose surrounding structure, the cylinders and crankcase inherited from a gasoline design, had already been asked to absorb about as much reinforcement as time allowed. It was a more forgiving path to a working diesel, even if, in principle, direct injection can be somewhat more fuel efficient. Caterpillar chose forgiveness and reliability over theoretical maximum efficiency, and under the deadline it was working against, that was almost certainly the right call. The supercharger that Caterpillar retained from the Wright design deserves a closer look too, because its purpose shifted subtly in its new diesel role. In the original gasoline aircraft engine, the supercharger's job was primarily about altitude, forcing enough air into the cylinders to maintain power as the aircraft climbed into thinner atmosphere, where a naturally aspirated engine would gasp and lose output. A tank, of course, never climbs to altitude, so that specific job vanished entirely in the conversion. But the supercharger found new relevance anyway, because a diesel engine benefits enormously from a strong, well-packed charge of compressed air, both to support the very high effective compression the diesel cycle demands, and to ensure the pre-chamber and main cylinder both received enough oxygen to burn the injected fuel completely and cleanly, without excessive smoke or wasted unburned fuel. Caterpillar's engineers geared the supercharger to spin dramatically faster than the crankshaft itself, driving it as a centrifugal compressor at a very high step-up ratio, packing the incoming air harder than the original aviation application ever required at sea level. This was not the supercharger doing the same job for a different reason. It was the same physical component inherited to save engineering time, repurposed entirely from an altitude compensation device into an integral part of the diesel combustion process itself, helping to guarantee that every one of the 9 cylinders firing in their rapid sequence around the crankshaft had the abundant, densely packed air charge that compression ignition needed to work reliably and to burn its fuel completely. One of the more remarkable features of the finished Caterpillar engine was not merely that it could run on diesel, but that it could run on almost anything. The RD-1820, as it came to be designated, was engineered as a genuinely multi-fuel power plant, capable of operating on diesel fuel, on kerosene, or on gasoline up to 100 octane, with only additives needed to adjust for whichever fuel was actually on hand. This flexibility was not an accident. It flowed directly from the indirect injection, pre-chamber design Caterpillar had chosen, because an engine that ignites its fuel inside a small, hot, turbulent antechamber is considerably more tolerant of fuels that resist self-ignition than an engine relying on direct injection into a comparatively cooler, larger open chamber. A fuel that might struggle to ignite reliably on its own in a main combustion chamber will often ignite readily inside the concentrated heat of a well-designed pre-chamber. The strategic logic behind this multi-fuel capability was straightforward and, in hindsight, ahead of its time. An American tank fighting in a foreign theater could not always count on a steady supply of the exact fuel grade its engine wanted. A diesel and only diesel engine solved the gasoline competition problem with the aircraft industry, but it created a new dependency on diesel specifically. An engine that could burn diesel or kerosene or high-octane gasoline with roughly equal indifference solved both problems simultaneously, giving the tank's crew and the supply officers behind them enormous flexibility in whatever fuel dump they happened to be near. It would be more than a decade before the United States Army formally adopted multi-fuel capability as a design requirement for its post-war tank and truck engines, and when it did, the RD-1820 stood as an early, largely forgotten proof that the idea worked. Converting the engine on paper was only the beginning. Building it in quantity required Caterpillar to construct an entire dedicated manufacturing operation, separate from anything the company had run before, and separate, crucially, from Wright Aeronautical's own production of the gasoline R-1820 for aircraft. The government formed a new subsidiary, the Caterpillar Military Engine Company, to run this effort, and ground was broken on a new plant in Decatur, Illinois, engineered to eventually reach a capacity of 1,000 engines a month. This separation from Wright's aircraft lines was the entire point of the arrangement. The diesel Radial did not compete with the B-17 program for engines, parts, or factory floor space because it was built somewhere else entirely, by a different company, using Wright's proven design only as an engineering starting point rather than as a physical supply chain. The first working prototype engine emerged from this new operation in January of 1942, remarkably fast given that ground had barely been broken, and testing began immediately at Caterpillar's own proving ground. By the end of 1942, a meaningful number of test engines had been completed, and 2 of them were already installed and running in actual tank hulls. The speed of this development, from a July 1941 request to running engines in tanks before 1942 was over, reflected both the urgency of the wartime timeline and the fact that Caterpillar had already solved most of the hardest underlying problems in its civilian tractor business, applying knowledge it already possessed rather than inventing an entirely new diesel engineering discipline from scratch. The first tanks built to carry the new engine were experimental vehicles designated the M4E1, built by Chrysler on the elongated hull and chassis of the M4A4, the same stretched hull that had originally been lengthened to accommodate the Chrysler multibank engine's own considerable bulk. This reuse was not incidental. The Caterpillar diesel Radial, once fully built up with its supercharger, transfer case, and cooling shroud, occupied a footprint roughly as large as the sprawling multibank it was being tested alongside, and only the longer M4A4 pattern hull had room for it. The first M4E1 began testing at Caterpillar's own proving ground in December of 1942, and by the spring of 1943, additional test vehicles had been sent out to Fort Knox, the Army's armor training and testing center, and to General Motors' own proving grounds for independent evaluation. The testing surfaced real problems, exactly the kind of teething trouble any radically converted engine should be expected to reveal under hard use. Engineers found difficulties in the gear train, the mechanical linkage carrying power from the engine's short radial crankshaft back through the new transfer case to the tank's transmission. They found clutch problems, the mechanism responsible for engaging and disengaging engine power proving unequal to the torque characteristics of the new diesel. And they found scoring between the pistons and the cylinder walls, a telltale sign of a diesel engine's harsher combustion pressures and different thermal behavior stressing components that had, after all, begun life designed for a gentler gasoline existence. None of these problems were fatal, all of them were fixed, but they were the visible evidence of exactly how much genuine engineering had to happen to make a converted aircraft Radial survive as a tank's compression ignition heart. And the fixes took time the war was not eager to grant. Once the problems from the M4E1 trials were resolved, the finished production engine, ultimately designated the RD-1820 by the Ordnance Department after Caterpillar's own internal designation of D200A, was a genuinely capable power plant. It displaced about 1,823 cubic inches, essentially unchanged from the original Wright Cyclone's displacement, because the cylinder dimensions that determined displacement were among the components Caterpillar had chosen to preserve. It produced 450 horsepower at 2,000 revolutions per minute, and more importantly for a heavy vehicle that spent most of its working life at far lower engine speeds, it delivered as much as 1,470 pound-feet of torque at a modest 1,200 revolutions per minute, an abundance of low-speed pulling power that a tank crew would feel every time the vehicle needed to claw its way up a slope or through soft ground. To move that power from the engine's short radial crankshaft to the tank's transmission, Caterpillar's engineers fitted an ingenious transfer case that stepped the output shaft speed up to 1.5 times the crankshaft's own rotation, a solution that let the compact radial engine still deliver the shaft speed the tank's existing drivetrain expected, without redesigning the whole transmission around it. In every meaningful respect, the numbers proved the conversion had worked. This was not a compromised, half-functioning experiment limping through trials. It was a genuine, capable diesel Radial built from an aircraft engine's bones, delivering power and torque that stood comparably alongside every other engine the Sherman had ever carried. With the engine proven, the Ordnance Committee moved to put it into series production. Chrysler was assigned to build the production tank at the Detroit Tank Arsenal, and the vehicle received its own official designation, the M4A6, joining the small family of Sherman letter variants defined chiefly by which engine sat in the tail. The production M4A6 differed in one significant way from the experimental M4E1 test vehicles that preceded it. Rather than reusing an unmodified M4A4 hull, the production tank combined the elongated M4A4 length chassis and rear hull with an entirely new large single-piece cast front hull section, a sharply angled nose designed to improve ballistic protection and to simplify the installation and later maintenance of the differential and final drive housed within it. It was, in its own way, as much a showcase of late-war Sherman hull technology as it was a showcase of diesel engineering. The first production M4A6 rolled out of the Detroit Arsenal and shipped on October 28 of 1943. Production continued only into the following winter, with the full run totaling just 75 tanks, a strikingly small number for a vehicle built at one of the most productive tank arsenals in the world. Part of the reason was cost. Each M4A6 carried a unit price of roughly $64,455, a substantial premium over the price of a standard gasoline-powered Sherman, reflecting the far greater manufacturing complexity of the converted diesel Radial compared with the simpler, longer-proven gasoline engines filling out the rest of the Sherman family. 75 tanks, each one carrying an engine that had begun life as an airplane's heart and had been rebuilt piece by essential piece to run on diesel fuel. Here, the story takes the turn that defines it, and it is a different turn from every other Sherman engine story. Because this engine was not rejected for being unreliable, and it was not sidelined by a doctrinal decision about fuel logistics the way the General Motors diesel had been. It was killed because the very company that built it was needed for something else entirely, something the war effort valued even more urgently than a diesel tank engine. Caterpillar's core business, building the bulldozers, tractors, and heavy earth-moving equipment that constructed airfields, cleared invasion beaches, and built roads for advancing armies, was itself one of the most critical contributions any American manufacturer made to the war. And by 1943, the War Department decided it needed Caterpillar's manufacturing capacity devoted to that core mission far more than it needed continued production of an experimental tank engine, however well that engine was performing. T.R. Farley, the executive vice president of the Caterpillar Military Engine Company, captured the situation with evident frustration in a statement preserved from the period. He noted that Caterpillar had been informed from high sources that its radial diesel engine was the outstanding power unit available for the Sherman tank, and that, despite this, the company had been directed by the War Department to bring the program to an early close, so that the manufacturing facilities it occupied could be freed for tractor production instead. Of the 1,000 engines that had originally been ordered once the M4E1 trials succeeded, only a small fraction were ever actually built, enough to power the 75 production M4A6 tanks and a handful of spares. 700 additional M4A6 tanks that had been ordered from Chrysler were canceled outright and reordered instead as the gasoline-powered M4A3. The Decatur plant that had been built from an empty field to produce this engine was repurposed for other manufacturing entirely. The engine had not failed. The factory that built it had simply been needed somewhere else for something the war effort judged even more essential. In one of the more quietly ironic footnotes of the entire Sherman program, the M4A6's real performance evaluation did not even begin until after the decision to cancel it had already been made. 10 of the 75 production tanks were sent to Fort Knox for formal testing beginning in March of 1944, months after Caterpillar's engine production had already been wound down and the factory redirected. In these tests, conducted essentially as a formality on a program whose fate had already been decided, the M4A6 demonstrated better fuel efficiency, greater operational range, and general performance that matched or exceeded every other standard Sherman variant then in American service. The diesel Radial, converted from a gasoline aircraft engine under enormous time pressure, redesigned at its combustion core while its structural skeleton was preserved, had turned out to work exactly as well as its designers had hoped. and the evidence proving this arrived only after the program that might have used it was already closed. It is one of history's small, quiet cruelties that the tests confirming the M4A6 was a genuinely good tank came too late to matter to anyone but the historians who would later go looking for the paperwork. The engine that Caterpillar's own vice president had called, on good authority, the outstanding power unit for the Sherman tank, proved its case in an empty courtroom after the verdict had already been handed down for reasons that had nothing to do with its merits. None of the 75 M4A6 tanks that Chrysler built ever saw combat. Every one remained in the continental United States, assigned to training duties, teaching new tank crews the fundamentals of driving and maintaining a Sherman on a power plant that would never accompany them overseas. Some served with the 777th Tank Battalion at Fort Knox for years after the engine that powered them had already ceased to exist as a production item. The Army formally classified the M4A6 as limited standard on May 3rd of 1945, days before the war in Europe ended, confirming what had already been true in practice for a year and a half, that this variant would never fight. And then the M4A6 simply vanished. Unlike the other Sherman variants, which survive today by the hundreds in museums and collections around the world, not a single M4A6 tank is known to exist anywhere. Not one example of the RD-1820 engine survives either. No test stand relic, no museum piece, no rusting hulk waiting to be restored. 75 tanks, each carrying an engine that represented a genuine and largely successful feat of wartime engineering, were built, used briefly for training, and then quietly scrapped, along with the record of exactly when it happened. The most complete conversion of an aircraft engine into a tank diesel that America accomplished during the entire war left behind less physical evidence of its existence than almost any other Sherman variant, a strange erasure for a program that by every test ever run on it actually worked. If the M4A6 itself vanished almost without a trace, the idea at the heart of it did not. The multi-fuel capability that Caterpillar had built into the RD-1820, the ability to run on diesel, kerosene, or high-octane gasoline with only additives to adjust, anticipated a design requirement that the United States Army would not formally embrace for another decade. Through the 1950s and into the 1960s, multi-fuel capability became a defining feature of American military engine doctrine, showing up in the power plants that drove post-war tanks and armored personnel carriers. Engines designed from the outset around the same flexible fuel logic that Caterpillar's engineers had arrived at almost by necessity in 1942, forced into it by the strategic need to solve two fuel problems: gasoline competition with the aircraft industry and diesel supply uncertainty overseas, with a single engine. The RD-1820 was, in this sense, a sneak preview of a philosophy the American military would not fully adopt until long after the engine itself and the tank it powered had been forgotten. It took the Army until the middle of the 1950s to get engine package size down, power output up, and manufacturing cost low enough to make widespread multi-fuel tank engines genuinely practical, more than a decade after Caterpillar had already proven, in a Decatur, Illinois factory built from an empty field, that a converted aircraft radio could do exactly that. The company that built bulldozers had reached into an airplane's engine and rebuilt its heart to run on almost anything, years before the rest of the American military establishment was ready to ask for precisely that capability as a matter of doctrine. In a war decided by what could be built and by what factories were needed most, the story of the Caterpillar diesel Radial is a story about an engine that solved its assigned problem completely and was canceled anyway. Caterpillar was handed one of the hardest and most specific engineering assignments of the entire American tank program. Not to find an engine, because engines already existed, but to reach inside a proven gasoline aircraft radial and rebuild its very method of catching fire. replacing spark ignition with compression ignition while preserving as much of the original architecture as the physics of diesel combustion would allow. The company kept the cylinders, it kept the crankshaft, it kept the supercharger repurposed for a new job, and it tore out and rebuilt from first principles everything that touched the violence of combustion itself: the pistons, the cylinder heads, the injection system, the lubrication, building a small pre-combustion chamber that used a controlled first burn to trigger a complete and reliable second one. The engine that emerged, the RD-1820, worked. It made real power and abundant torque. It ran on nearly any fuel a supply officer could find. It powered 75 production tanks that later testing proved were, by several measures, better than the standard Sherman they were built alongside. And none of that mattered because the war effort needed Caterpillar's factory floor for bulldozers more urgently than it needed a diesel tank engine already being adequately served by General Motors and Ford. The program was not defeated by German engineering, and it was not defeated by American doctrine. It was defeated by its own manufacturer's success at something else entirely. A company so essential to building airfields and clearing roads that the war could not spare its factory for the very engine that factory had proven it could build. In a war fought between industrial systems, sometimes the hardest problem was not finding a solution, but finding a factory that could be spared long enough to build it. Caterpillar solved the harder problem, the engineering one, completely. It rebuilt an airplane's heart to beat on diesel, kerosene, or gasoline alike, and it did so in barely a year and a half from a standing start. What it could not solve was the simple arithmetic of wartime priority, which decided that the hands and machines capable of building that engine were needed more urgently building something else. 75 tanks, no survivors. An engine that worked in a war that had already decided it did not have room to let it keep working. That was the whole story, and it was, in its own quiet way, one of the strangest and most completely erased successes of the entire American war effort.